Yeah, glad to see a lot of faces here. Seems like a pretty good turnout, and excited to be here with you all today. I'm Jerry, co-founder CEO of Llama Index, and the title of this talk is Building Advanced RAG Over Complex Documents. So I have 90 minutes with you all. I've never done a 90-minute talk before, or technically this is like a workshop. I don't know if you all have like laptops or something. I have like 2 Jupyter notebooks that we could try to all collectively run through. Fingers crossed that it doesn't break. I tested it like an hour ago. But we'll kind of go with the flow and see how it goes. But the overall purpose of this talk is, many of you have probably built RAG systems, some in production. A lot of this is going through the key concepts to basically build a full, complete end-to-end RAG pipeline from the data side to the query side, and especially over complex data, right? And what does that really mean? And so we'll go through some basic principles. Many of you who have followed our content, for instance, on socials, might have seen some of these concepts already, but we'll go through this in just like a sequence of slides, as well as some notebooks that basically demonstrate some of these core concepts. Okay, let's get started. So the overall agenda today is that we're going to go through a few components. First is we'll talk about this overall idea of building a knowledge assistant. 2 is giving an overview of RAG, right? Many of you are probably already familiar with the basics, but we'll talk about the basic pipeline and then talk about where it goes wrong. And then we'll talk about 2 main categories to actually improve your RAG pipeline. The first category is improving data quality. So basically, figuring out how to make the proper data decisions, parsing, chunking, indexing, to actually try to improve your data. What does complex data even mean? We'll try to define that. And then we'll also talk about improving query complexity. So basically, going from naive RAG towards building a general QA interface that you can apply on top of any data so that a user can ask any question and get back the correct answer, right? That really is the overall promise and extends a little bit more than some of the basic setups that you see today with like top K vector search and so on and so forth. Each of these 2 components, number 3 and number 4, will have like a little mini workshop, like Colab notebook. So feel free, there's like a QR code attached. Feel free to like scan it and follow along, or you can just like follow the slides. I'll try to share this like maybe more publicly as well, share the materials. A lot of these use our native Databricks LLM integration. So if you're like a Databricks customer, you can directly plug this in as part of your notebook or your production application. Okay? Let's get started. So within the enterprise, there's a few key use cases that we've seen from talking to a lot of different developers working in different verticals and different company stages. So this includes knowledge search and question answering, which is really like the use case behind RAG, right? RAG is really more just like a conceptual framework for getting there. But the overall use case that as a company you want to build is you want to build some overall like question answering system over your unstructured data, but then also extend that into your semi-structured data and structured data. A lot of people these days are building chatbots, stuff that can maintain your conversations over time. Many people are starting to explore agents. So these autonomous engines that can not only synthesize information, but actually perform actions for you over time. And then, of course, just on a pure document level, there's not just this idea of you ask a question, get back a response. There's many types of different document workflows you can employ. Here we mentioned tagging and extraction. There's other workflows sorry, I'm not sure what's going on. Give me one sec. Okay, we're back. There's other workflows like being able to do structured data extraction from your document, do summarization, among other components. Okay, we will wait and see. Okay, it's back. For the purposes of today's talk, let's talk about this idea of building a knowledge assistant. And so, per the previous slide, this overall idea is that the human has some task or input question. It wants to query a knowledge base, and then it wants to get back an answer, right? It's a very simple concept. But really, this takes the central idea of RAG and extends a little bit beyond that. Because think about the types of questions that you can ask. You could ask very pointed questions, like what is X in this specific point in time, or you could ask a very generalized task stuff that's either a multi-part problem or something that's very vague and actually requires a lot of planning and task decomposition to actually solve it. Either way, there's some interface where you want the user to specify that task or input and get back the answer. And that's the overall purpose of this talk, is to show you some of the concepts that actually build this knowledge assistant. So, as mentioned here, build an interface that can take in any task as input and give back an output. The input forms could include very simple questions or pointed questions about specific pieces of the data. It could include complex questions like multi-part questions. It could also include longer running research tasks. The output forms could include short answers, so stuff that's just like it returns a response in a simple paragraph. It could return a structured output, or it could return an entire research report. So that's the overall goal, right? And we'll talk about RAG and how it fits in. So Retrieval-Augmented Generation. We've heard this term many times throughout the course of the past year and a half, and it really consists of two main components, right? There's data parsing and ingestion, and then data querying. The data parsing and ingestion piece is interesting because it fundamentally represents like a new type of ETL that you're applying on top of your unstructured data. The promise of RAG is that you can just dump in your entire bucket of PDFs and somehow get the LLM, no matter what LLM it is, whether it's closed or open source, to generate an answer over that data. And so being able to process, parse, and index that data is a first step, and we'll talk about some of the components there and how you can make that better in just a bit. The second step here is data querying, right? Where you treat, once the data is actually in a storage system, like a vector database or SQL database or a doc store, you can treat it as an API interface so that the LLM, you can orchestrate some sort of flow over that data and orchestrate it with other tools to basically achieve the use case that you want to solve, right? So if it's just like chat over your data, that's the only data interface that you're using. If you actually have like other tools or services that you're using, you can combine those along with the vector database as a tool interface to basically orchestrate your overall application. Many of you, when you're first starting out building a RAG pipeline, have probably built what I call naive RAG. Naive RAG is something that you can basically follow and get something up and running for like 5 to 10 minutes by following our quick start tutorial or the tutorial of any other framework out there. It usually consists of something like the following. If you're a Python developer, you use like an open source toolkit to basically load in some document. Let's say you have a single PDF document. And then you do some sort of splitting on top of that document. So you do, for instance, like sentence or paragraph splitting with a chunk size that's predetermined. And then you put it into a vector database. And then these text chunks, they're embedded and stored in the vector database. And then during the retrieval time, you just do like top K retrieval, like top K equals 5, top K equals 10, whatever. And then you take all that data and then you stuff it into a prompt, like a simple question answering prompt, right? And the prompt typically looks something like, here's my context, and then you take all your retrieved context and stuff it into that prompt, and then here's my question, you take your question, and then feed this entire prompt to an LLM and get back an answer. Some of the core challenges with naive RAG include the following. They tend to work well for simple questions over a simple small set of documents. For instance, if you have a single annual report by, from Tesla or any other tech company, or our classic like benchmark data set like the Paul Graham essays, if you ask a question about a specific paragraph in that data, naive RAG tends to do pretty well because these days, embedding search, being able to match on the semantics of a given piece of text, it's not bad. And so if you have a question about a specific fact, you're generally able to retrieve it. And then because the LLM can see that context in the prompt, you're able to synthesize a proper answer. However, productionizing RAG over more questions and a larger set of data is a lot harder, right? And so let's walk through some of these failure modes that you might encounter. Some of these failure modes include, one, asking simple questions over complex data. So if your data is not just, we'll define complex data in just a bit, but roughly speaking, let's say it's not just like a text file with a bunch of text. It's a document that contains a lot of different sections to it, like images, tables, charts, and figures. How do you actually properly synthesize information over this multimodal data almost without hallucinations? There's also this idea of being able to ask pointed questions and scaling your retrieval quality up as your document corpus gets bigger. It's fine to build a naive RAG solution over 3 PDFs, but how do you actually build RAG over 10, 100, 1,000, even 1,000,000 documents of various types? And then, going along with this overall theme, how do we ask not just pointed questions, but more complex questions that are multi-part in nature and can actually, you can actually answer the entire question by iterating over your data in step-by-step fashion to basically solve this entire task at hand. If you're an enterprise, really how this relates to business value or the end use case is that your goal is you want to build some either internal or external QA tool. And one of the top priorities we've seen from any company is to basically get back high response quality from any set of questions that you anticipate your users asking, right? There's many other, of course, use cases of LLMs. For the purposes of this talk, we'll just really think about how do you get back really good response quality from any sort of question you might want to ask. And if you think about it, naive RAG is pretty boring, right? What you're really doing with the LLM, with a naive RAG pipeline, is the only thing you're doing is you're just putting stuff in a prompt and synthesizing that information. So you're really only using it once to give you back an answer, and it's really a light layer on top of an existing retrieval system that has already existed for many years before ChatGPT. And so in this setting, it's really just a glorified quick lookup system or glorified search system. And there's a lot of different types of questions and tasks that naive RAG can't actually give an answer to. So the overall topic is, can we actually go beyond simple search and question answering to building this more general context-augmented research assistant? So the two main focus areas of today's talk is going to be two components. One is improving data quality. So taking your unstructured data, we'll focus on unstructured data for today, go through a data parsing, ingestion, processing layer, put it into some sort of storage system. And then the second component is improving query complexity, where given a question, you're able to retrieve relevant context from that question, put it into your prompt, and then get back a response. So let's get started on the first topic, improving data quality. If you were here last night, for instance, at the Mosaic X meetup, you might have already seen this slide. But the overall principle that I want to emphasize is that RAG is really only as good as your data, right? It's a similar principle as traditional machine learning, where this overall idea can be encapsulated by this expression, garbage in, garbage out. But good data quality is a necessary component of any production LLM app. And it's very intuitive. If, for instance, you have very messy or misformatted context, if your context is just missing, if the ground truth is missing from the prompt you send to the LLM, even if the LLM itself is very good, you're not actually able to get back a proper answer. And we've seen this even with the latest models with GPT-4, GPT-4o, Opus. And so one step that you really need to do in ensuring production RAG is actually having this data processing layer to go from your raw data through this data processing layer to clean data in order to build some sort of production LLM application, right? Question answering, chat, copilot, autonomous agents, and more. The main components of this data processing layer include the following steps. It includes parsing, being able to load the data from a file. So if you have a PowerPoint, if you have a PDF, being able to actually parse out some information from that data. Being able to actually properly transform that data. And what we mean by transformations these days, especially in the context of RAG over unstructured data, is really just chunking, right? And then so being able to chunk your data in good ways, and then figuring out how to take that data and then put it and index it into some sort of storage system, right? And there's actually different types of ways you can index stuff beyond just using pure vectors. A classic example is actually using metadata along with your vectors. You can also index things by some sort of knowledge graph, putting things in a doc store so you can do different tiers of retrieval over that data. But there's a lot of different components of data processing. And I think the one overall idea I want to highlight here is that what we're basically inventing here is some sort of like new ETL stack, right? Like if you think about the traditional data engineering workflow of taking in some data, it requires a lot of human effort to be able to write the SQL statements, transformations, to go from raw unstructured data, doing some extraction on top of that with say like small fine-tuned trained ML models, and then going from like different stages of your tables in like Delta Lake or whatnot to basically transform it from raw data to process data for your BI use cases. Here, it's honestly a little bit more standardized, and it's both simple but also requires a bit of consideration. Because you are able to, if you do this well, just dump in a lot of unstructured data without a lot of human effort. But the trick is you basically need to make sure your parameters for this data pipeline are well tuned to achieve good performance over your data. So there's a lot of information in these slides, but I want to go through some general principles, which is one, parsing. We'll elaborate a little bit more on parsing like throughout the rest of the slides as well as in the notebook. But one consistent theme is that if you don't have good parsing, you're going to run into the garbage in, garbage out problem, right? And especially if your document has like badly formatted text and tables, oftentimes they confuse even like the best language models. The second piece is chunking. So there's a few general tips for chunking, some of which I've realized I forgot to put down in the slides. But the overall, some core principles for chunking is one, try to preserve like semantically similar content. I think Greg Camera has like this famous tweet on the 5 levels of like text splitting. So you can go from like token level splitting to kind of slightly more adaptive like paragraph level splitting to semantic chunking by actually arbitrarily defining, or not arbitrarily, defining the chunks more smartly based on the embedding similarity with the previous sentence, and then doing some sort of like agentic splitting. These are all general techniques, but the overall idea is that you want to preserve like semantically similar content as much as possible. One thing that does lead to bad performance is if you have relevant text that's at the boundaries of a chunk. So for instance, a relevant snippet is getting cut in half. If you only retrieve one of these snippets but not the other, then you're just missing information. And then oftentimes the second snippet is never retrieved because it never actually has the like relevant metadata or context to actually be retrieved in the first place. Another general thing that's typically a pretty strong baseline is this idea of page level chunking. So page level chunking basically just means you take in a set of files, you split it into pages, and then each page itself is just a chunk, right? This is honestly a pretty strong baseline. I think if you're building like a RAG pipeline, it's one of those things that I would probably encourage many of you to just like try out. Stop worrying about tuning your chunk size of like 512 or 1024. These days, especially as like models get cheaper and costs are coming down, just try to stuff entire pages into the prompt. And the reason is the way we write documents these days is we try to preserve a lot of content in like bite-sized pieces in pages. We have a strong incentive to try to like maintain a bunch of information there, whether it's PowerPoint slides or just like essays or PDFs or reports in general. And so we actually found that this, even before some sort of fancy chunking, is a pretty good baseline to get started. There's also kind of a more future-related discussion of what is the impact of multimodality, right? We've all seen, the GPT-4o demo. Many of us have probably used GPT-4o as well as the latest models. All natively support multimodality, like Gemini as well as Claude. And so an interesting thing to think about is, are chunks natively going to be just images going forward for documents, or do you also still want to represent them as text? With some of the tooling that we've provided with Llama Parse, you're actually able to do both. You're able to represent your data both in a multimodal fashion as well as in a text-based fashion. But it's also one of those things where right now, image-based chunking does introduce significant cost and latency trade-offs, but it's something to think about as these models inevitably get better and faster in the future. Some general principles around indexing include the following. A lot of people these days oftentimes just embed the raw text and directly feed that into the embedding model to get back some sort of vector representation. A better idea is that oftentimes, instead of just like embedding the raw text, like if you embed a table that's going to have a lot of numbers in that table, is to embed a lot of different references to that table. You can still embed the raw table itself, but maybe embed like an extracted summary, or embed the caption, or all three of the above, and basically link all of them to the same underlying data. Another version of this example is you do page-level chunking, right? But then you embed every sentence. And so especially for weaker embedding models that don't have too many dimensions, you're able to embed like, say like, the 100 different sentences within this page, but then link it all back to the source document. So you decouple the indexing and the synthesis a little bit. So what this means is that when you embed things, you embed a smaller version of that overall content, but during synthesis, you feed like the entire page into the LLM before you get back a response. So the overall idea here is that having multiple embeddings point to the same chunk is oftentimes a pretty good practice, right? And basically, it's one of those things that allows you to optimize retrieval a little bit separately from how you're optimizing the synthesis piece, because you're giving the LLM as much context as you possibly can. The topic of this talk today is over complex documents, which we've talked a lot about on our socials. But we think that a lot of documents or data, especially unstructured data, can be classified as complex. So complex data includes basically any document with a bunch of the following, like embedded tables, charts, and images. So like if you have a PowerPoint presentation, not only are you going to have a table like this, you're also going to have like spatially laid out text in a bunch of different positions. You might have like irregular layouts in a PowerPoint or even in a PDF. You might have different types of metadata floating around like headers, footers, page numbers. But really, there's a lot of just these different types of content within a document. And a lot of times when you try to do some more like naive chunking, you either lose information or you're not actually splitting the information in the right way. So a lot of times naive RAG indexing pipelines can fail over these documents. And so one of our examples here is to show you how to build like an advanced RAG indexing pipeline. Part of the reason for this, and just doing a little bit of a deep dive, is that most document parsing, especially stuff that's existed in the past, it wasn't really designed to minimize LLM hallucinations. Let's say, and also some of them are just like not amazing because you're not paying for it. Like PyPDF is fully open source. Of course, there's many other paid APIs as well that are a little bit better. But let's take this table right here. PyPDF is going to extract this table into a bunch of like messy text and numbers. And you can see this basically like there's some text representation here that basically shows what the parsed output looks like. And it doesn't look very nice aesthetically. But beyond that, what's actually happening is not only does it not look nice, it's also actually missing information under the hood. For instance, sometimes if there's like a missing value in the table, it's collapsing it into one row. Maybe it's shoving like two columns together. And what ends up happening is, one thing we've observed is the more that this happens, the more kind of like information chaos and loss there is in the data, the greater the likelihood of some sort of hallucination by the LLM. And even in very powerful models, if you ask the right question, oftentimes it's going to confidently give you back the wrong answer. So one of the things that we've spent a lot of time on is this idea of just like, document parsing, but native to LLMs. And so that's where we came up with Llama Parse. Llama Parse is a special document parser designed to let you build RAG over complex documents. We came out with this a few months ago. We've had a decent amount of just grassroots adoption since then. And basically, we opened this up as an API and started basically adding a lot of support for different types of complex data workflows. So some of the core capabilities include table and chart extraction, and we'll run through an example with Llama Parse in just a bit. Being able to actually input like natural language parsing instructions. Being able to extract out images, both like, if you have an image within the document, you can extract that out separately, but you can also extract out like an entire page as an image from a document. And we also support just like a bunch of different document types. We support PDFs, PowerPoints, docx files, XML, and recently, actually, Excel files as well. If we have a little bit of extra time at the end of this section, I'll show you the kind of like some fun Excel examples I came up with. So you can't see this here, but roughly speaking, an example of what this looks like is we took the Apple annual report for, I think, 2023, and we basically built a RAG pipeline over the entire report. And as a test, we try to ask a question over every cell in this table. This is just like the net sales and expenses and income and all that stuff, right? And so with llama parse, we actually found that we're able to get back, like the greens basically mean that the RAG pipeline we built using this parser returned the right answer, and reds means that it gives back the wrong answer. So when we ask, a bunch of these questions over every cell of the table, like what is like the net product sales in September 24, 2022, it'd be like this. You see we actually get most of these answers correct with one incorrect value right here, or two. There's two incorrect values. With most other parsers, like PyPDF, PyMePDF, Textract, PDF Miner, again, these aren't comprehensive benchmarks, so take it with a big grain of salt, right? And so I'm sure there's plenty of other benchmarks where we still have like room for improvement. There's just a lot more reds, and basically what this means is that using at least the default settings that we tried, it's extracting out the data in a way such that LLMs couldn't quite chunk and represent it, so that when you fed it into an LLM, or one, it either wasn't being retrieved, or two, when you fed it to an LLM, it wasn't being synthesized. So the first piece is that that I want to convey is llama parse on its own is actually a decent baseline, even if you don't do advanced indexing and retrieval, right? But once you actually combine some of the key capabilities of just a llama parse document parsing, or just in general like a good document parser, whether you use us or other providers, is just you should combine like advanced parsing with advanced indexing and retrieval to build a performant RAG pipeline. So first step here is you use llama parse to parse a document into a semi-structured markdown representation with like text, tables, images, or we also support JSON mode as well, so you can return your outputs in either Markdown or JSON, some sort of semi-structured format. Once you're able to actually model your document in kind of like specially delineated like text, tables, images, then you can use some sort of like parser like algorithm to extract out like the text and table and image chunks. And what you basically get is some sort of like document graph, right? So if we visualize a little bit, you might have like a text chunk right here. This says like SQL database, but let's just forget about that and pretend it represents like some table in a PDF. This cell right here might represent like an image. And all of these can be represented as what we call in Llama Index a node, right? So a node is just like a representation of some underlying object that is being indexed and embedded. And oftentimes a simple thing that you can do is you take each of these tables or the images and you pass it to either a text or multimodal model to extract out a summary from this object. And so now each reference to an underlying table or image is a summary, whereas the reference to the text chunks could be the raw text itself, it could be another summary, it could be the sentences, so on and so forth. So you have some sort of like hierarchical indexing scheme going on right here, where like this layer is the layer of nodes that are being indexed, and this layer is the raw data, whether it's like text, images, or tables. So you use llama parse to extract out this underlying set of objects. You use maybe like an LLM or use some algorithm to extract out the set of nodes that's going to be indexed. And then these are the nodes that are going to be dumped into a vector store. And then this data you can either store in the vector store as well, or you could store elsewhere, right? For instance, if it's an image, you might want to put it into some sort of object store system, but still maintain a reference from the node to the underlying file. An example of how this works is, we basically built this overall pipeline, and actually, I think in the Colab notebook that I'm about to run through, you'll be able to see this in action. You can ask a question like, over like a 10K document. In this example, in the Colab notebook, it's going to be a PowerPoint. But basically, you can ask a question over some value in a table, right? And in the annual report, you're going to have a bunch of different like text, tables, charts. And let's say you ask, like, what is the repayments of debt and the cash flows from financing activities for Netflix? The baseline or naive RAG pipeline is going to give you back the wrong answer. It's going to say like the repayments of debt and cash flows is not provided in the given information. Part of that is actually might be due to the fact that it's not getting actually retrieved because the indexing or embedding representation of that is bad, right? And so this partly relates to why I think some sort of advanced indexing scheme on top of your data makes sense. You have a lot of different references that are better representations of the underlying content than just embedding the raw text. But here, with the kind of advanced parsing, but also indexing retrieval engine that we've created, you get back like the repayments of debt and the cash flows ended this year is 500,000, right? And so this is indeed the answer. I know the year is like cut off, but this is the correct answer that you're supposed to be looking for. Another fun example that I'm not really going to run through, but basically is that Llama Parse is powered by Gen AI or LLM models. So in contrast to traditional document parsers, you can actually prompt it, right? Similar to an LLM. I'm going to go through this Colab notebook really quick just to show you what this looks like. But you can roughly like take in some sort of comic book. So I'm going to go in here and see if I have the actual manga loaded up as well. But basically, let's see. Okay, there's some manga like this, right? It's like a cartoon, and then there's also math. How many of you can give me a definition of a derivative? All right. So basically, we took this document, and then we ran it through Llama Parse. And the default like vanilla parsing gives you back like a table right here. So you can see it, it tried to extract out these symbols, like the limit and epsilon, Greek letters, as like the actual ASCII characters, right? But what we really wanted is we wanted to extract out the math formulas in LaTeX. And so we basically gave it a prompt. So the core line to look for right here is output any math equation in LaTeX Markdown, right? So we gave it back to Llama Parse, gave it some parsing instructions, and then we were able to, so this is without instructions, this is like the previous results. And then with parsing instructions, you're able to get back LaTeX. Right? How many of you have written in LaTeX? Okay, many of you. So you probably know what I'm talking about. It's basically just like a bunch of specialized syntax for representing math. And so this is exactly what we're able to do. And what's the benefit to you guys? Basically, you get a little bit more flexibility in your parsing. If you have a complex piece of data, there's actually an example that's pretty cool, like an insurance document with like claims. You can actually use this prompt to basically annotate each claim with like whether or not it's covered or not, because the table is like massive and spans like 10 different pages. And so if you actually just even did the naive like chunking, you would not actually retrieve or know that like this specific thing is like not covered by insurance. Whereas like with parsing, we're actually able to attach all this like metadata on top as it actually parses the data. So just interesting feature to check out. There's also, again, I won't run through this, but like JSON mode, which relates to this idea that you can actually model these very complex PowerPoint documents as both text, but also images. One recent thing that we started supporting is what we call GPT-4o mode, which allows you to use GPT-4o under the hood to basically, one, extract out the text, but also return the images to you natively so that you can actually plug it into your multimodal RAG pipeline, right? So you not only index the image via like something that's getting embedded, but in the end, the synthesis is also being done by GPT-4o. And the specific example that we're going to talk about today is this idea of like RAG over PowerPoints, right? So over a PowerPoint presentation, we'll walk through just an overview of what that slide deck looks like, and then basically use Llama Parse to And then the llama index open source toolkit to build like some sort of RAG pipeline that can answer questions over this data. Okay, how many of you guys have laptops? Okay, a decent chunk. It's totally fine if you don't. Just follow along the slides. I'll try to run through this. Fingers crossed, I'm like kind of YOLOing this, so let's go. Basically, here's a mini workshop on let's build a RAG pipeline with Databricks LLMs and local embeddings. You should be able to scan this QR code to basically get back the Colab notebook. Let me just double check this real quick. And there's also, I'll be clicking this link in just a bit to walk through it. Okay, I'll give it like 10 more seconds. But the overall idea is that, we are going to go through. I just realized this might actually be a little hard for you to follow along because you would also have to go to Llama Cloud to sign up for an API key if you haven't done so already. But all the resources are basically in the notebooks. But anyhow, we'll just, at least you have like the links to basically bookmark and put in your browser for later. Okay, let's run through this. So I'm going to open up this notebook right here. And I think it is this one. So I already preloaded this. And I'm going to read the introduction. But basically, the cookbook is to basically use llama parse plus the llama index open source library to build a RAG pipeline over financial PowerPoints. And so we are going to do the following. We are going to run the first cell where you just pip install a bunch of our libraries. And so specifically, the 3, maybe 4 things to just keep in mind is there's the llama index core package, which is just our framework for helping you build different types of LLM apps over your data. We've versioned out every single integration into a separate package. So we do have a Databricks LLM integration, and so it's just going to be here. And the second thing that I realize is hard is like if you don't have a readily available Databricks API key, it might be a little bit harder to follow along because you have to spin up like a cluster and get that API key. But also, we're going to use local embeddings from Hugging Face just as an example. So this just downloads the model locally. We're going to use a small model that can run on your computer. And then we're going to pip install the llama parse client library. It interacts. It's a Python SDK for the overall service. And then we're going to install the following packages just for parsing PowerPoints. Okay. Cool, so I already ran this pip install, but we're gonna go through and basically go through, set up cells to basically go through and define the API keys and whatnot. And we're going to be using the following models. So on Databricks, we have, Databricks provides access to a bunch of different LLMs. This one is Databricks Llama 3, 70 billion. You can use whatever model you want, but this is with the current cluster, and then we're going to be using BG small as the embedding model, right? In Llama Index, we have integrations with a lot of different LLMs and embedding providers. One thing you can do, especially helpful in a notebook setting, is if you don't want to pass these 2 objects around to basically whatever your downstream flow is, you can just set a global config in the settings. And so we're going to run this. Okay, I think it is trying to download the Hugging Face model, which is why it is taking a little bit of time. However, in the meantime, we are going to take a look at, importing llama parse. So we just have to run this. And then we are going to take a look at this slide deck. And just to give you a sense of what this looks like, we are going to run this. And then I'm going to show you just this data. So this is just a sample financial statement slide deck. You can see this is what it looks like. A lot of different text. There's like some tables. There's some more tables, some text. This is actually a pretty simple deck. I think there's going to be other ones that many of you probably already have that are a lot more complicated than this. But Okay, so this is the data that we're going to be using for indexing. Right. To use Llama Parse, if you haven't done so already, you are going to need an account on Llama Cloud. So basically, it's just cloud.llamaindex.ai. We integrate with like your Google account, your email, and just rough information. I won't go into it too deeply, but you get 1,000 pages per day, and for free, basically. If you sign up for the paid plan, you actually get 7K pages per week for free before we start charging, and it's 0.3 cents per page. So pretty cheap for PDF parsing, but anyways, that's what it is. And then we're going to download this data, right? And then we are going to go through, and then first we're going to do a baseline. In LlamaIndex, without Llama Parse at all, if you just want to get something working, just for free, this is why we installed all the like PyTorch, like Pillow packages. There are like free PowerPoint loaders out there, and that's actually baked into what we call like the simple directory reader, where you can just like load in all your data. So once you actually load these documents, I'll show you a little bit about what it looks like. Right, this is what you get from using like a more naive parsing approach. And while this is running, you're also going to be able to run through Llama Parse to basically see what this presentation looks like, or to basically see what the parse document looks like. I'm just going to have that running. In the meantime, while it's running, we already preloaded the outputs, and so if you take a look at one of these tables, right, in the keynote slides. I think it is this one right here. Is it? Five, 2, 6. Maybe this one. Oh, this one, yeah. So basically, you can see that the parse table is in like a markdown format, right? And so what this is important, right? Because if we take a look at the standard like non-Llama Parse slides, it's going to look like this. And then change the index right here, and then this is going to be like 17. Okay, never mind. This is basically what the slides are going to look like. You can see with a naive parser, the text tends to be a little bit more messy. You can see like the slide number is actually listed right here, slide 17. It doesn't quite parse the output of these slides in a way that you can actually use. Like a lot of the information is dropped, right? Whereas with Llama Parse, I'm just going to go through the Llama Parse documents. This is what it looks like, and I'm going to zoom out really quick. But you can see the PowerPoint's parsed in this manner. We parse out any sort of like tabular information in more well-structured tables. One property, by the way, for an LLM is that they tend to be trained decently on like well-structured data. So if you actually make the effort to structure your data, they have a much better time understanding it. That's just like a general principle to follow. Okay. So we parse out these documents, and then now we can basically build both the baseline query engine as well as the Llama Parse query engine. One nice property of just like using LlamaIndex as an open source library is that if you don't really want to think about the indexing or tune it, you can basically get back some sort of RAG pipeline over your data in 2 lines of code. It's literally just like load in vector store index up from documents and then do add query engine. Of course, there's going to be a lot more tuning you're going to need to do to actually bring this to production, but this is good for a demo. So we're going to have like vanilla query engine as well as a Llama Parse query engine. So this one, again, is using the naive RAG pipeline of just naive parsing, and this one is using Llama Parse, right? And so we're going to ask these these questions to the 2 pipelines. We're going to ask, what was the liability provision as of December 31, 2021 to these 2 pipelines. So we're going to run it through the query engine. That's the naive pipeline. And then we're going to run it through the advanced llama parse pipeline. The liability provision, if you go back right here, is basically here, right? It's this thing right here, 1910, December 2021. It's the liabilities provisions. And obviously, because the parsing is incorrect, you're not able to get back the right answer. But here, you're actually able to get back the correct answer. So not a lot of fancy things going on here, right? This is honestly like the orchestration side is primitive. It's still the naive RAG pipeline. Like you just use an LLM, like synthesize the information. But part of this talk, like the first part, really was emphasizing that with like proper data quality, you actually can improve your indexing, embedding, and retrieval to make sure you actually answer questions over complex data. So this basically covers the simple questions over complex data category, right? It doesn't quite cover the complex questions over, like multiple documents. And so that's actually the part that we're going to get to next, right, in part 2. Okay, cool. So let's go to part 2 of this workshop, which is now that we've talked a little bit about data quality and being able to parse different types of content in different ways, we can now talk about improving query complexity over your data. So we go back into thinking about what are the different classes of questions that you might want to ask over your data. And there's certain questions we do want to ask where naive RAG pipelines might fail, right? So some examples here include like summarization questions, like give me a summary of like the entire document, the entire contract, financial report, all these different things. You might want to compare document A, document B, if you have like 2 resumes, if you have 2 financial reports. We see this a lot actually when we talk to prospective customers on just being able to ask these types of questions over multiple documents where they want to look at the differences between the 2. There's also maybe questions that blend in your knowledge of unstructured data along with like structured metadata or annotations that you have stored somewhere. And then you also have like general multi-part questions, like stuff that's either very vague in scope or inherently contains multiple parts. And so, we recently did a course with Andrew Ang on this with deeplearning.ai, but we thought a lot about really the relationship between RAG and also agents, which, these days, many of you are probably building agents. Many of you are at least thinking about agents. A lot of developers are thinking about what are the proper abstractions, tooling I should use to basically build different types of agentic workflows. And one of the core use cases still remains this overall idea of knowledge synthesis and question answering. And so we approached it from that lens and really thought, what are the layers we can add to some sort of standard RAG pipeline to make it more agentic and sophisticated at query understanding. So a traditional RAG pipeline has the following downsides. It's one single shot. It really only uses the LLM once. 2, there's no sort of query understanding or planning going on. You're just directly feeding that question to a vector database and doing retrieval. 3, there's no tool use. And by tool use, I mean you're not actually inferring the parameters of anything. The LLM is not figuring out how to call an API interface. That API interface is fixed. It's just a vector database, and you're directly passing in the query. There's no sort of like self-correction or being able to like refine your steps over time. So there's no like reflection error correction layer. And there's also no memory. There's no state being stored. That can actually be pretty helpful from like a programming perspective because then it's a little bit easier to test. But in a lot of times in like a conversation setting, you're not actually remembering like back and forth conversations. So a full-on kind of like agentic system, can be arbitrarily complicated. It really depends on how you define it. But it tends to have these properties. It typically is a little bit more multi-turn. There's some sort of like query or task planning layer. There's some sort of like tool interface for interacting with external tools so that you can treat the vector database as just like one tool amongst like other tools that you might want to interact with, whether it's like a data warehouse, whether it's like calling Salesforce or something, or just interacting with different types of services like a calculator function, code interpreter, so on and so forth. There is usually some sort of reflection layer, like being able to actually validate the responses as it's being generated, seeing if it's correct, and making kind of like game time decisions on what to do if things aren't quite what you expected. And then there's also some memory layer, right, for personalization. Some of these things, honestly, like agents is a very broad topic. Many of you are probably thinking about agents from a bunch of different ways. There's a lot of resources there on building like multi-agent systems. A lot of this is probably worth like many like 90-minute workshops. And again, I think for the purposes of this, I think we'll primarily think about how to apply agents or just like some sort of agent system to this idea of like knowledge synthesis and question answering over your data. And so, going along with some of the core ingredients that we talked about in that Andrew Ng course is there's agent ingredients, and then there's what I call like full agentic systems that you can build. Agent ingredients are kind of components that you can pick and choose and basically apply within your own workflows. They tend to be a lot more simple and limited in functionality. The advantage is that it's much easier to test. They're oftentimes more reliable. And many times you actually, instead of building a full agent system, want to more explicitly define some workflow over your data that you have visibility in and can control, right? So the agent ingredients include the following. They include being able to basically do like routing and tool use. Tool use is basically just routing, but it can infer parameters. So basically you can do some function calling over a set of API interfaces to understand like what parameters to call these tools with. There's doing some sort of like query planning or query decomposition breakdowns. There's a lot of different classes of just like query transformations these days, right? From chain of thought to hide to some sort of like step back prompting to some sort of like sub-question like decomposition. And then there's also just a memory module. You can have a memory module without anything else in an agent. Basically, it just maintains state, stores conversations over time. And then there's like full agent systems that basically operate as like a cohesive whole, right? There's like a very standard one that's been around for like at least a year. Is just this idea of like a React power agent. You give it some tools, you give it like a reasoning loop, and it can basically iterate through these tools like step by step. And then there's more interesting agents that have a lot more like dynamic planning execution capabilities. So going through some of these, we'll talk about routing, right? Routing really is just an LLM prompt that is a multiple choice picker. Given some task, pick the relevant set of choices, like whether it's one choice or multiple choices that are the best fit for this input. And it's a very simple form of agentic reasoning. It's basically tool use without the parameter inference. And so one classic example of just like what you could use routing for, right? A lot of times when people think routing, you can actually use this too, but like you think about like model routing, for instance, like being able to route a given request to the right model, depending on like the complexity and the cost and latency and those things. I think that's basically related to this idea, but typically in that idea, you use a much cheaper model. In this one, you're actually just using an LLM for routing, and so oftentimes a good way to think about it in the context of like question answering is depending on what type of question that is or the complexity of that question, pick the relevant like retrieval pipeline or strategy to basically answer that question. Oftentimes you might not need to do like retrieval over the entire document if you want to answer a pointed question, but if it's like a summarization question, you do need to go through the entire document to analyze it, analyze the entire thing holistically. Another component is like conversation memory. And this is one of those things that you probably need to add to your pipeline. It's not necessarily like coupled with the rest of the agent components. You don't need memory with like tool use and planning. You could just have memory on its own on a RAG pipeline, right? Like the vector database, the retrieval interface could be totally fixed. And you just have like a memory module as a component that stores like the user's conversation history over time. I think we have some of these capabilities, like core memory modules that you can use. Honestly, I kind of like had some conversations with some folks too. Most people, like at the baseline that you're probably using is just like storing some chat buffer of your conversation history, right? Like just being able to store like a rolling window of the current conversations and just dumping that into the prompt. There's some more interesting memory modules coming out these days with like vector search or like knowledge graphs and these things. But I think we're still like not quite there in terms of standardizing on what exactly is a good indexing and storage architecture for like conversations are flowing over time, right? And it actually tends to be a little bit separate from just the way we think about RAG these days, which is like indexing a static source of data. Indexing conversations, extracting out concepts over time. It tends to be a little bit more dynamic, free-flowing, and I think people are still coming up with like the best abstractions there. But anyways, you have some memory module, and there's ways that you can basically just plug it into a RAG pipeline, right? You just like directly inject the conversation history as part of the prompt when you do synthesis. And then the next component is query planning. There's a lot of, like I said, different components or pieces or like ways to do query planning. It is a component of an agent. Like if you have an agent, you do want it to plan, right? Plan out like a DAG of steps, plan out a tree of steps, all those things. But just on its own, query planning is really just about breaking down some sort of like complex query into more parallelizable subqueries, right? So each subquery can be executed against like, sorry, this is just like one component of query planning. Like every subquery can be executed against any set of like RAG pipelines. Like this is a version of like query planning that we call like sub-question decomposition. Given like a multi-part question, see if you can break it down into, like a bunch of questions in parallel. They can then launch against like different pipelines. There's also other types of planning. This includes like hide, like being able to hallucinate like an answer and use that to do retrieval. Doing some sort of like step back prompting, which is like given a question, take a step back, ask a more abstract question, see if you get back an answer there, and use that to inform the answer to generate. There's also, of course, just like chain of thought, like think step by step, break this down into sequence, and try to use that to answer a question. And then, tool use. Tool use is actually something that is quite interesting because a lot of models these days are supporting function calling. And the more models that can natively support function calling and do it well, then the more agentic behaviors there will be, right? The more like developers will be incentivized to basically build agents. Tool use fundamentally is using an LLM to basically call an API. If the LLM doesn't have function calling support, then you can basically just prompt it. Like, you just directly write in the prompt. Here's like the function signature of a bunch of tools that I have. Please pick the right tool for the current task at hand, and then try to pick like the right parameters, basically call this tool. These days, a lot of models, OpenAI, like Anthropic, Google, like Mistral, like a bunch of open source models are starting to support like just native function calling APIs. Which is good because what this means is that the model's actually fine-tuned. Like you give it a parameter, you actually just give the function signature into the LLM, and then it can natively like pick the right function to pick without you actually having to figure out what the prompt is to give it. And so, like we're gonna show this in the workshop notebook in just a bit. That one actually doesn't use function calling because it's using Llama 3 70B. And so as a result, it actually doesn't work all the time, right? So it's a little stochastic, but that'll be fun. We'll see if it fails or not. But basically, tool use is one of those components, though, and it's going to become a more prevalent feature as LLM development goes forward. A lot of the ways that we think about RAG or text-to-SQL can actually reduce to tool use. Like in normal RAG, it's basically like function calling without actually using the LLM to infer anything, because the interface is just a vector database. There's this concept called like auto retrieval, self-query, like depending on how you call it, where you use like a question, or given like a question, the LLM can infer like the metadata filters of the vector database along with the semantic query to pass in. That is basically tool use on the vector database. Imagine you have a function signature of the vector database containing metadata filters as well as the text. You using the LLM to infer what those metadata filters should be is basically treating that function or like having a view in that function and figuring out how to call that through tool use. There's also like text-to-SQL, right, which many of you might have built. Text-to-SQL is basically tool use, but the like prompt or the doc string that you give it is like, write a SQL statement that captures like this or translates this query into something you want to execute against a SQL database. So when you put all these agent ingredients together, you basically get back like a full agent system with query planning, memory, and you get back like a full agent system. It contains query planning, memory, tool use, and also potentially contains like additional components like reflection, some sort of just like multi-agent system even, And then we can also add some additional bells and whistles like controllability, observability, so on and so forth. So, this is just a diagram showing the same thing. Once you have this full agent system, how many of you are familiar with React, by the way? Just doing a quick show of hands. Okay. So, I think many of you are. And so basically for those of you who aren't familiar with it, React is, again, just the way of sequentially iterating through your tools to basically do chain of thought prompting, given a complex question, figure out what's the best next step to take, what's the next action to take, given the previous steps that you've already taken. So it's basically next step prediction and tool use. And that's probably the simplest agent reasoning loop. Whether it's React, where you're explicitly prompting the LLM to think step by step and do tool use, or a version of React that is much simpler for you to implement is if the LLM supports function calling, just do a while loop and just keep calling the LLM with the sequence of function calls and user messages you've already done to basically see if the LLM natively decides to pick a new function or complete the response. So this is basically sequential reasoning, right? You're not trying to reason the entire pathway of how to solve this thing at the very beginning. You're just trying to reason the next step, and you're going to go in somewhat of a greedy fashion until you get back the proper response. The second agent reasoning loop is DAG-based planning, which is more a little bit more dynamic, right, than just pure sequential reasoning. DAG-based planning means that somehow, even at the very beginning, you try to plan out an entire DAG, right, or a graph of steps to take to basically get back to solve the task. And so this introduces a little bit more strain on the LLM because it basically forces it to think multiple steps ahead and plan out almost like a tree of sorts that converges instead of just planning out the next step. We find that most LLMs aren't actually that good at DAG-based planning beyond say 4 or 5 steps. But nevertheless, there's some agent papers recently that basically incorporated this approach and basically optimized it in a systems level to basically create a more efficient agent system than pure React-based approaches. A classic example of this, for something that could use a DAG is if we go back even to the query planning example, what is the revenue of Uber and Lyft in 2021, DAG-based planning will allow you to basically treat those two as we can just parallelize the calls instead of actually having to think step by step. So that type of thing is a little bit more efficient than just pure sequential next step reasoning. And then the third is basically an extension of DAG-based planning, except it's a little bit more stochastic because you're uncertain of the future. You can't actually reason until the end, so you're going to try out a bunch of things and see what sticks, right? The classic example here is basically imagine you're playing like AlphaGo, right? Imagine you're playing Go or chess or Dota or something. You don't quite know the entire sequence of steps that's going to lead you to victory or solve the task at hand. But what you're going to do is you're going to plan out a set of possible next steps, and then define a value function on each node. Over time, as you get more experiences and observations, basically backprop the rewards onto the node. And then until you eventually get to the final goal state and basically solve the task. If you're familiar with RL or reinforcement learning in the traditional deep learning ML sense, this is very familiar. And it turns out you can roughly basically do something with LLMs as well, just kind of in the text-based through text-based reasoning. This is probably the least explored topic. I think there are some interesting papers that have come out recently on how to do just better tree search and through an uncertain environment. But it's something that at the same time is also a lot more expensive cost and latency wise. Okay, so I basically just went through all this stuff already, but basically I already mentioned sequential reasoning. You can do React, chain of thought, and tool use through prompting, or a function calling loop. These are probably the basic things you should start with if you're building some sort of agents, right? Not talking about some sort of more constrained workflows where you're just using the LLM to do a simple prompt. If you just want an agent system that's easy to use, just use React or function calling, give it some limited set of tools, 2 or 3 tools, and try to just iterate on this action observation sequence until you solve the task. An example of DAG-based planning is LLM compiler from last year. which basically does what I talked about. It plans out an entire DAG of steps, so it maps out like dependencies between different nodes. So if your question is how much does Microsoft's market cap need to increase to exceed Apple's market cap, you're going to plan out like this entire set of steps. Like A equals search Microsoft market cap, B equals search Apple market cap, C equals like do a math function on like A over B, and then like D equals like an LLM call on top of C, right? That's planning out a DAG because it's basically like two arrows from A, B, and C, and it converges on like it converges on D, and then you get back the answer. The nice thing about planning out something like this is that anytime you have like a set of like parallelizable edges, you can basically launch async jobs, so it makes it a lot more efficient. And if you have some sort of like efficient executor or scheduler, then you can basically run this entire thing as a system a lot more efficiently than just like sequential next step reasoning. We have this actually as a Llama pack in Llama Index. We also introduced like a structured planner agent, which basically takes this concept and makes it a little bit more general. It does introduce like certain cost and latency constraints, right? That's kind of like an overall theme, is the more sophisticated the agent reasoning is, the more cost and latency there will be. And then the third piece is this idea of like, just generic like tree-based planning, where given something that's like super vague and not well scoped, let's just like try out a bunch of states and then like, and then smartly like decide between exploitation versus exploration until we solve the task. A class of like recent papers like Tree of Thoughts, Reasoning via Planning, like Language Agent Tree Search, and a bunch more this year have basically started to explore this idea. In general, we actually implemented this in Llama Index as well. If you're trying to do this in a question answering use case, just know it can be a little bit unreliable just because it's not quite there yet. Like the model capabilities aren't quite there yet, where if you're doing like a long running sequence of trying to like maintain a bunch of different states at once, the models oftentimes gets tripped up and confused as to what next state to pick. But it is a very promising thing to try out, especially as models, again, get better at reasoning, especially if GPT-5 comes out and as costs come down. And I think Andrew Yang had a tweet on this as well, but self-reflection, right? It is a necessary component of your agent system. And basically, self-reflection is around using feedback, whether it's human or automated, to improve your agent execution and reduce errors. So actually adding this layer throughout different parts of your agent or RAG pipeline, and actually I can be more specific. You can have self-reflection on the retrieval layer. So when you return a bunch of nodes, you can actually use maybe a lightweight LLM to judge the validity of every piece of retrieved context, basically perform like a re-ranking filtering pass. You can also do some sort of self-reflection as a whole loop. You run the entire like RAG pipeline once or agent system, look at the response, see if it actually answers the question, and then give back feedback into the agent to say whether it is or is not helpful to basically help refine the trajectory. These are just like simple things that you can do, and oftentimes you can do them with more lightweight models. There's actually some interesting open source models that are approaching GPT-4 in capability and evaluation and judgment. An example is like Prometheus, or Prometheus 2 actually, that we also have an example on, where basically it's fine-tuned for evaluation. And so it's a very interesting use case of using like smaller modules as these lighter weight eval steps in the middle of your entire agentic system. And of course, there's some like additional things that you probably want to do. These days, there's, well, obviously you want observability, you want to see the traces, you want like maybe some lower level control, the ability to kind of like go forward, go backwards in time, being able to customize your agentic logic. There's a lot of like talk about multi-agent systems these days, right? Which, to be honest, like we don't, we're still like developing something that's like a little bit more fleshed out in Llama Index, but at the same time, there's a lot of great frameworks like AutoGen, CrewAI. There's other ones like LangGraph as well. And basically, the rough like categorizations of these multi-agent workflows are kind of the following. One is like some sort of synchronous flow, being able to define like an explicit flow between agents. And two is some sort of more like async freeform flow, where you treat each agent as a microservice that can communicate with each other. And instead of you explicitly defining the pathway to follow, you give the agent a lot of leeway in deciding what's the plan that it should take, which agent to call next, and in order to solve the task, right? And I think more people these days are probably leaning towards the former, which is also why we have this overall diagram. Like, I think more people are probably taking in, going all the way back, like just these agent ingredients and composing more explicit systems from these where you can actually observe and see what's going on, then kind of just like trusting a full agentic system to do its job. That said, as models get better, we see the latter part happening more and more. Okay, so before I actually go into the second workshop and just make sure that we basically take a quick breather, is if you're an enterprise developer, you're interested in some of the capabilities that Llama Cloud has to offer. For background, Llama Cloud is our enterprise offering. It includes parsing. It also includes kind of like indexing, retrieval capabilities to fundamentally centralize knowledge across your unstructured data and eventually semi-structured and structured data for your LLM application. Whether you're building RAG or agents, if you want to kind of like somehow tame all the massive sources of data that you have and feed it to your LLM, come talk to us. We love to chat. Llama Parse itself, by the way, is fully self-serve, so we don't need to talk if you just want to use Llama Parse. It's available on cloud.llamaindex.ai. You can sign up for an account and basically just start using it. Cool. Okay, in the last how much time do I have? Like 15 minutes or so. Let's try to extend the RAG pipeline into an agent. And so we're going to go through this notebook. And actually, I don't know how many of you have done the deep learning course. It's actually pretty similar to that, just a little bit scoped down, right? And so we're going to use Databricks LLMs, and we're going to basically build like a research agent with Databricks. So I think I'll share the slides a little bit more publicly afterwards as well. But basically, we're going to go through and pip install all our favorite libraries, the Databricks LLMs, Hugging Face embeddings, and then next is we're going to do the basic setup stuff. So I'm going to import my API key and all these things. It's probably not the most secure thing to do, but that's okay. Trust you guys. You'll be monitoring my Databricks build the next few days. And then I'm going to copy my cluster ID. Don't look. Okay. So we're going to go through the same process of just doing the LLM and embedding model setup. And the overall task for this, it's a little bit different than the previous one, which was the financial report example. For this one, we are going to download 3 iClair 2024 papers and then parse them using Llama Parse, and then feed them to an agent. Okay. So we're going to download 3 papers that were at iClair 2024, MetaGPT, Long LoRa, and also Self-RAG. Many of you might have already read these papers, but they're good reads, definitely recommend them. And we're going to download them as PDFs. The next piece is we are going to use Llama Parse and basically define a function to basically load the information from these documents. Okay, so we loaded this information from these PDFs. The next part is, similar to basically taking some of the concepts I just talked about, like RAG is really just, like an agent without tool use. We're going to convert all these RAG pipelines to tools. Okay, so we're going to define a function called get.docTools, which one constructs a RAG pipeline from each document and basically treats every single document as its own tool. The second, maybe nuanced piece is for the vector search, we're not just going to directly call the vector database or call the vector like a naive RAG pipeline as a tool. We're going to wrap it as this overall function that contains query as well as page numbers. So if you want, it will actually, the LLM can actually infer the relevant page numbers to call the function with. because we're going to provide this as a function signature for the LLM instead of just the raw vector search, just like passing the query through. So if it takes in the question and calls this function, it'll pass in both the query as well as any relevant page numbers. And then the doc string is defined in Python, but with some of our abstractions, the doc string is also a prompt that you're giving to the LLM. So you can see it's basically used to answer questions over a given paper. Leave the page numbers as none unless there's like a specific page that you want to search for. The reason the doc string is written this way is because, again, it's a prompt that we're actually going to feed to the LLM. So under the hood, this function is very simple. All it's going to do is just call the whatever vector index or pipeline that we set up with metadata filters. And for each document, we're going to define two tools. One is that vector search tool that takes in page numbers as input as optional, and then also a summary tool. So you can get back, if the question actually asks for a summary of something, we'll get back call that to basically retrieve the entire document as context to answer the question. So let's run that, and then we're going to get the tools, which is going to build a pipeline for everything, and then I'm going to input my llama parse API key. All right, let's just do this. Okay, right here. So it's getting the doc tools for MetaGPT, for Long LoRa, and also self-RAG. And then the overall framework is we are going to set up an agent over these three papers by basically treating each of these documents as tools, right? This isn't necessarily the recommended agent architecture, just taking a step back. I'm just kind of showing this as an example, but it is an agent architecture that you can think about. The only downside of this, by the way, is if you have, I don't know, 100 papers or something, then you have 100 tools for agents. And we all know that the more tools we stuff an agent with, the less effective it becomes. There's ways to get around that, basically. For instance, you can treat the tools as chunks in the vector database, dynamically construct tools on the fly to basically just always feed the agent some relevant set of papers as tools, depending on basically what the query is. But there's other architectures that you probably set up where you basically have the agent over a single tool, and that tool, the function signature, is a lot more defined, where you can actually specify the paper name to call. But in any case, we're gonna, it's still indexing these documents, and we're gonna feed these tools to a React agent worker. Because we're using Llama 3 7db, it doesn't have native support for function calling. So we are just going to use a plain React cycle given a set of tools to basically answer questions over. Okay, it's still taking a little bit of time, but I think it's done now. And then we are going to take these tools, feed it to an agent worker, and then we are going to ask a question. And what's immediately going to happen is I'm going to hit Databricks rate limits because basically when you feed in when you use the summary query engine, it actually calls basically the LLM API all at once because it breaks down the document into a bunch of chunks and then feeds them all simultaneously to the LLM. And so you can see oftentimes there's some retry errors. And of course, okay, this doesn't work. I'm going to try something else. I'm going to try what are the MetaGPT comparisons with ChatDev described on page 8 of the MetaGPT paper. If this works, this hopefully is a nice demonstration of basically the function calling in action. And if it doesn't work, I have the outputs pre-cached over here. So why am I getting TOS? Okay. Cool. So it's running right here, but we can basically see what the pre-cached output would say, which is, to answer this question, the MetaGPT comparisons with ChatDev, one is I'm obviously going to use the MetaGPT tool, right? And so we're going to be using, I think my API key might be wrong, the vector tool defined over MetaGPT. What are the MetaGPT comparisons with ChatDev described on page 8 of the MetaGPT paper? But we see the page numbers is also specified as 8. And so this is an example of because we defined that Python function to take in not just like the semantic query, but also the page number, then we can basically apply that as metadata filters on the vector database. And so like, I think the outputs are actually cached below, so this is okay. But you get back a more precise result this way, especially if you're able to specify things that you can actually run through metadata filters. And the response, if you take a look at the sources, which isn't shown here, but if you take a look at the sources, you see that all the relevant chunks are going to be from page 8 and not from other documents. So it's a very simple example, but auto-retrieval is one of those abilities that allows you to more precisely filter for relevant context in a given document. The next example is compare the complexity of the approaches in self-RAG and MetaGPT, the two different tools, and which approach uses more tokens. This is an example of a multi-part question where you take in something that's very complex and break it down into smaller steps. So to take in this question, we're going to basically first query the self-RAG tool, and then also the MetaGPT tool. With, honestly, a little bit more powerful of a model, it would actually break down this question into, how does self-RAG actually work and how many tokens does it use. Here you see it didn't actually do a lot of breakdowns over this data. It just passed in the raw question. But it's okay, because basically once you actually synthesize all this information and get back the response, you see that like MetaGPT is a more complex approach that likely uses more tokens, etc. Cool, and I think that was basically 82 minutes. And so, going back into this, hope some of this was useful. To summarize, we ran through both the data quality aspects of making sure you have a proper data pipeline set up for RAG, to even if you're doing something very basic and naive on the RAG side, to be able to get back a decent answer for any questions you want to ask. And then being able to actually orchestrate some basic agentic workflows over your data to answer more complex questions. Have the QR code here if you want to chat about Llama Cloud, which is the overall service. But yeah, I don't know if there's questions, but happy to answer any questions if that's a thing. Yeah, thank you.